Let's start this video by building on the material that we discussed in the last video about quotient rings and ideals to prove the first isomorphism theorem for rings. So recall, this is the first part of theorem 7 from section 7.3 of Dummit and Foote, and says that if phi from R to S is a ring homomorphism, then the kernel of phi is an ideal, the image of phi is a subring, and R mod the kernel is isomorphic as a ring to the image. Okay, so we already proved in the previous lecture that the kernel of phi is an ideal of R. And we also proved that the image of phi is a subring of S. So the only thing that we need to do is show that R mod the kernel of phi is isomorphic to the image of phi. So for notational convenience, let's let I be equal to the kernel of phi. So the only thing that you need to remember to make this proof work is what the isomorphism is from R mod I to the image. And it is, you have to take the left coset of I containing R and send it somewhere. And that somewhere needs to involve phi in some way. So the easiest thing that you could try would be to send R plus I to phi of R. And that works. That is a ring isomorphism. Okay, so the proof consists of justifying that sentence. Why is this a ring isomorphism? Well, first, kernel of phi is an ideal, so R mod I is a ring. That's the first thing that, like, you know, if you want a ring isomorphism, it must be a map from a ring to a ring. So you have to first do this whole part from the first video that says that R mod I really is a ring whenever I is an ideal. Okay, then rather than show you 1, 2, 3 checking that this actually is, or I guess really just 1 and 2, that this map really is a ring isomorphism, I just want to show you, like, why is this true? Well, the operation in R mod I, the addition operation, says R plus I plus S plus I is R plus S plus I. And then think about what happens over on this side. Because phi is a group homomorphism, we know that phi of R plus phi of S equals phi of R plus S. And you'll see that the thing you need to check that, like, this operation, this map behaves well with respect to addition is exactly given by these two statements. Same thing with multiplication. We know R plus I times S plus I is RS plus I. And over on the other side, phi of R times phi of S is phi of R times S, because phi is a ring homomorphism. And again, when you're checking that this map is an isomorphism, these two statements together give you exactly what you need to show that this map is going to be actually be a homomorphism of rings as well, that it'll respect multiplication. So what's going on here now is that this is a bijection between rings. Why is it a bijection? Well, what is the fiber above some element in the image? It's exactly a coset of I in R. So this really is a bijection because of this cosets R fibers statement. And it's a group homomorphism, and it respects multiplication. So all of these things taken together is a ring, says that this is an isomorphism theorem of rings, which proves this result. So I'll leave it as a little exercise for you to go from this discussion here to, like, a fully rigorous proof, or you can look at the details in Dummit and Foote. Okay, so I'll pause and erase, and then we'll prove the second part of theorem 7 from section 7.3 that we opened this lecture with, which is this statement that every ideal is the kernel of a ring homomorphism. Let's now prove the second part of theorem 7 from section 7.3 of Dummit and Foote. Let's say I is an ideal of R. We have this map pi, which goes from R to R mod I, defined by pi of R is the left coset of I containing R. This map is a surjective ring homomorphism, and its kernel is I. So every ideal is the kernel of some ring homomorphism. this homomorphism is the natural projection of R onto R mod I. All right, so let's prove this. I is an ideal, so R mod I is a ring. So in particular, it's a group. And for groups, we talked about this a long time ago. This is this natural projection homomorphism for groups. It is a group homomorphism, and the kernel really is I. All right, so what do we need to check then to see that this is a ring homomorphism? Oh, also, it's clearly surjective. So we just need to check that it respects multiplication, meaning that pi of Rs has to be equal to pi of R times pi of S. Why is that true? Let's just write what both of those things are. Pi of Rs is Rs plus I. It's the left coset of I containing Rs. Pi of R is R plus I. Pi of S is S plus I. And now we just need to see that Rs plus I equals the left coset of I containing R times the left coset of I containing S. But that is exactly how multiplication works in this ring R mod I. So this is by the definition of the multiplication in R mod I. Okay, so that's the end of the proof. So the next thing that I want to do in this lecture is, when talking about rings, we spent all this time talking about definitions. So whether or not a ring should have a 1. If your ring has a 1, does the subring need to also have a 1? Does it need to be the same identity? And then if you require your rings to have 1s, what do you require about a ring homomorphism? Okay, so I want to take these two results. This first result, this ring isomorphic or first isomorphism theorem for rings, and this second result, that every ideal is the kernel of some ring homomorphism, and ask, well, what happens if your definition of ring homomorphism changes? Like, is this statement still true? What happens with the isomorphism theorem for rings if you have a slightly different notion of what it means to be a ring or a subring? So that's what I want to emphasize, is how do these statements change if you change your perspective on what these definitions are? That rings must have a 1, a subring R prime of R must have an identity as well, and it must be the same as the identity of R, and that a ring homomorphism phi from R to S must send the identity of R to the identity of S. And I will just give you the answers by citing them to a document of Conrad called Properties of Ideals. So I'll pause and erase, and I'll write down the relevant statements, and I'll point out the only really, really small places where you have to write down like one extra sentence in these arguments. So the short answer is that these two statements change in exactly the way that you would expect, and the proofs change by adding one sentence about what happens with the identities. Let's talk about two results from Conrad's notes on properties of ideals. First is theorem 3.4, which says every ideal is the kernel of some ring homomorphism. So it's exactly the same statement as the statement we just proved. The only difference is that the definition of ring homomorphism here has an extra property, that the ring homomorphism must send the multiplicative identity of the first ring to the multiplicative identity of the second ring. So how do you deal with this? Well, if R has a 1, so does R mod I. So it's not only a ring, but it's also a ring with unity. This is easy to check. The left coset of I containing the multiplicative identity of R satisfies all the things that you need to be the identity of R mod I. Okay, so now you know that both of these rings have 1s. So you just need to check that this same natural projection of R onto R mod I that we used to prove this theorem before, that natural projection is still a ring homomorphism. And it is. You just check that where does it send the multiplicative identity of R? To the left coset of I containing this multiplicative identity, which is the identity of R mod I. So this is still a ring homomorphism, and the rest of the proof is exactly the same. All right, so let's go back now and think about how does the first isomorphism theorem for rings change? Well, it says if phi from R to S is a homomorphism, and let me point out that Conrad talks about ideals mostly in this document. And dealing with ideals in non-commutative rings is significantly more complicated because now it's not necessarily true that a left ideal is automatically a right ideal like it is in commutative rings. So this theorem is stated for commutative rings, but everything about it is true for any kind of rings. So I just want to point that out for when you look this up. So if you have a homomorphism of rings with kernel I, then R mod I is a ring because the kernel is an ideal, and it's isomorphic as a ring to the image of phi, which is a subring of S. This is something we proved last time, that even with this additional requirement that a subring has to contain the multiplicative identity of S, this is still a subring. And these two rings are isomorphic, and the isomorphism is given by the function that takes the left coset of I containing R to phi of R, that it's the same map that we used to prove this earlier in this lecture. Okay, so what's the only difference? This map still group homomorphism that respects multiplication, so we just need to check that it takes the multiplicative identity of the first ring to the multiplicative identity of the second ring. So image of phi is a subring of S. We proved this last time. That means because it's a subring, the identity of the image of phi is the identity of S. And what do we know? Because phi is a homomorphism of rings, phi sends the multiplicative identity of R to the multiplicative identity of S, which is the multiplicative identity of the image. So if you take the multiplicative identity of R mod I, which is 1 plus I, where does it get sent? To phi of 1, which is the identity of S, which is the identity of the image of phi. So it seems like there are a couple of steps here, but every statement is following directly from the definition of what it means to be a subring or what it means to be a ring homomorphism. So what am I emphasizing here? Even with these slightly different definitions, these theorems have exactly the same statements, and the proofs are exactly the same plus a sentence about what happens with the multiplicative identities.